Good evening, RAG. This is the ABC of stellar evolution. And as you can see from the subtitle, we're going to be looking at the birth, the life, and the death of stars. So we know that when we look out into the universe, we see probably billions, maybe even trillions of galaxies, and they all seem to contain many, many billions of stars. Some of them are isolated, some of these galaxies are interacting with neighbouring galaxies, some of them have rather different structures, like this rather magnificent barred spiral. But it seems like all of these galaxies contain, as well as a fair bit of dust and gas, they all seem to contain stars. So stars seem to be everywhere in the universe. And this particular talk is looking at where they come from and how they live. So we'll be looking at the birth, the life, and the death of stars. What's going on in the middle of the star, how they come to be, in other words, how the nuclear fusion that ignites the star starts off, and we'll be looking at the life of a star and the balance between radiation pushing out and gravity pulling in. Live fast, die young is the mantra for various stars, including the more massive ones, and we'll see how that's a little different for less massive stars. And we'll be asking the question, what happens when they come to the end of their life? What happens when the nuclear fuel runs out? Does a star die with a bang or a whimper? And what's left after a star goes supernova, or in the case of less massive stars, what happens when the fuel runs out and it simply dies with a whimper rather than a bang? And we'll finish by thinking about if gravity wins out in the ends, we end up with a black hole. So let's just remind ourselves, looks like we have some people in the lobby. Okay, let's remind ourselves of the life cycle of the sun, just as a sort of reference point, if you like. So here's a timeline, and the left-hand side, 0, is the Big Bang, approximately 13.8 billion years ago. So we are currently 13.8 billion years on from the Big Bang. I'm not going to talk about the Big Bang itself, or looks like we have somebody else in the lobby. So I'm not going to be talking about the Big Bang and the origin of where all the material came to make the stars, but I'll be coming to that point shortly. We think our sun was born somewhere around there, about 9 billion years after the Big Bang. And our sun is middle-aged because we are approximately halfway through its life. We think its life will be about 10 billion years or so. And once the sun starts to come to the end of its life in another perhaps 5 billion years, it's going to swell up into a red giant. Eventually, the outer atmosphere of the sun will be shrugged off, leaving a small hot star that we call a white dwarf. This particular cartoon, bear in mind, none of these sizes are to scale. This is just to give us an idea of what is going to happen to our sun. Stars that are less massive or more massive may not go through the same cycle. So I'll be explaining why our sun will become a red giant and what a white dwarf is in a little while. So what's going on at the heart of all stars? Well, in the core of a star, when the pressure and temperature conditions are right, which effectively means when the pressure and temperatures are high enough, then it's possible to fuse hydrogen into helium, and that releases energy. Hydrogen, well, we're not talking about atoms here because the nucleus of an atom will have lost its electrons in a very hot environment. It'll be a plasma, meaning a whole load of positively charged protons, which are the nuclei of hydrogen atoms, and a whole load of electrons floating around as well. And when the temperature is high enough, it is possible to push protons together such that hydrogen turns into helium. So this is what it looks like in a sort of cartoon. We can take 4 protons on the left-hand side, and if we squeeze them together hard enough, we can make a nucleus of helium. which is actually made of 2 protons and 2 neutrons. We're going to ignore the fact that 2 of those protons seems to have changed. All we're going to say is that it takes 4 hydrogen atoms or 4 hydrogen nuclei squeezed together to make 1 helium nucleus. And in terms of the total amount of material we're talking about, every second of the sun's life, 620 million tons of hydrogen is converted into 616 million tons of helium. And I'll be coming back to what's happened to those 4 million tons that appear to have been lost. So every second of the sun's life, a huge number of protons are converted from hydrogen into helium. So stars are not simply nature's way of lighting up the universe. They are, if you want to think of it that way, fusion factories. They are factories that basically take hydrogen made in the Big Bang and fuse it into heavier and heavier and heavier elements. Now, I know I'm not dealing with that question of where did the hydrogen come from in the first place. I'm assuming simply that it is there. The hydrogen was made in the Big Bang, and of course it's a very good question to ask, well, how did the Big Bang make all the hydrogen? But that's not the topic of this particular talk. We're simply assuming that the Big Bang did take place. It made shed loads of hydrogen, and stars have been converting hydrogen into heavier and heavier elements ever since. So we can ask the question, if we start with hydrogen, where do all the stars come from? Well, you may not realize this, but anybody can make a star. It's actually quite easy. You just have to follow these 5 very easy steps. Step number 1, start with a very big cloud of hydrogen. Step number 2, wait. Step number 3, wait some more. Step number 4, wait just a little bit longer. And step number 5, well, there isn't a step number 5. You now have a star. So effectively, if you start with enough hydrogen, gravity will collapse that hydrogen cloud and make a star. In effect, you don't have to do anything else. You just leave it alone and it will get on with that. So here's a big cloud of hydrogen, the Orion Nebula, or the Great Nebula in Orion. A very large cloud of hydrogen, many, many light years in diameter. Right at the heart of it there in the very bright white area, that's where stars are being born. So what is it that triggers star formation? If you start with a big cloud, what is it that actually triggers the process? Well, there are giant molecular clouds floating around the Milky Way. And what do we mean by a giant molecular cloud? Well, it has a number of properties. A giant molecular cloud, they're called that, well, because they look like clouds. They consist mainly of hydrogen molecules, and perhaps you can see where I'm going with this. The third property is they're quite big. Tens of light years across, possibly even 100 light years across. Much bigger, remember, than the typical distance between stars, which is a few light years in the Milky Way. So if we have these giant molecular clouds floating around the galaxy, what is it that triggers the process to make them collapse and form stars? Well, we think there are a number of possible triggers. One is that the clouds might collide with each other. They're all independently orbiting, just like all the stars are, around the centre of the Milky Way. Every once in a while, one cloud will collide with another, and when 2 clouds collide, that could be enough to trigger the collapse of one or both of the clouds. It's also possible that shock waves ripple through the cloud and trigger its collapse. And these shock waves might come from, for instance, the death of another star. If a star goes supernova, it can produce shock waves that ripple through a cloud and trigger star formation. So it's quite possible that the death of one star, which we haven't come to just yet, can actually trigger the birth of others. And another reason why a giant molecular cloud might collapse and form stars is because galaxies collide. That sounds fairly apocalyptic to talk about one galaxy colliding with another, but it's actually a perfectly natural part of galaxy evolution. When we look at a galaxy like this appears to be a galaxy isolated from many others, and perhaps you can see in the spiral arms there's little blobs of pink every once in a while. Pink is the characteristic glow of hydrogen. So whenever we see a little bit of pink in a galaxy picture like this, it's probably because there are clouds of hydrogen in that region. And when we see a galaxy not in isolation, but interacting with some of its neighbours, we often find even more blobs of pink, indicating that there are more star-forming regions whenever a galaxy interacts with its neighbours. We see that most dramatically in this case. Here's the antenna galaxy, so called because of these tidal tails that are coming out as these two galaxies interact with each other. But if we look in more detail at what's going on in this region with an image from the Hubble Space Telescope, we see again an absolute riot of new star formation, very strong regions of pink, indicating that as these two galaxies are interacting with each other, and as you can see on the left, distorting each other quite dramatically, there are large areas of pink indicating that there are large areas of new star formation. The Milky Way galaxy is going to collide with the Andromeda galaxy, or at least it's probably going to collide. There's some controversy as to exactly whether they will collide or whether there will be a near miss. But in this animation, we're going to see what happens when Andromeda and the Milky Way come close to each other. Top left is M33, the Triangulum galaxy, which is just a spectator in this collision. When two galaxies collide, it's very unlikely that any given star is going to hit another star, but all of the gas and the dust is going to interact, and the gravity of one galaxy will distort the other. And you can see these two galaxies pass through each other, and then eventually they settle down into one very much larger galaxy. Probably an elliptical galaxy. In other words, the spiral arms of both galaxies, the Milky Way and the Andromeda galaxy, are going to be disrupted. If we think what that looks like from our perspective, if we imagine that the Earth is a place where we can watch this collision, well, that's what the sky looks like at the moment. The Milky Way, as seen from the inside, is the band of light across the sky, and over on the left there near the top we see the Andromeda galaxy. In a few billion years, the Andromeda galaxy will be a lot closer. So for those of you who like photographing the Andromeda galaxy with a camera and a telephoto lens, bear in mind that if you decide to wait for a little while, you won't need a telephoto lens, you'll need a wide-angle lens as Andromeda hurtles towards us. In about 3 or 4 billion years, Andromeda galaxy will occupy a huge chunk of the sky. And shortly thereafter, the galaxy will pass through the Milky Way. And so at this point, about 4 billion years into the future, there is going to be an absolute riot of new star formation. When you look into the sky, it'll be impossible to figure out which stars belong to the Milky Way and which stars belong to the Andromeda galaxy. There will be large areas, as we see here, of pink or red, indicating large clouds that are new star formation. Let's have a think about what happens in more detail in one of those clouds. This might look like a star, but it's not. It's a large cloud of hydrogen that's been put into a simulation. Computers prefer large spherical clouds rather than a big cube, which might seem more logical. It's simply easier to compute if you start with a large spherical cloud. So it's not very realistic in that clouds are very ragged and not perfectly spherical, but this will do for the simulation carried out at the University of Exeter. So we start with a large cloud. It's not perfectly uniform density hydrogen. We've got lots of little blobs of hydrogen, a little more dense here, a little less dense there, and we've given each little bit of hydrogen a random velocity in a different direction to simulate what it would actually be like for a real cloud in the galaxy. And then the simulation simply lets gravity do its stuff. and gravity will pull on every part of the cloud, and let's see what the simulation tells us. The colours indicate that the yellow is more dense than the red, and some parts of the cloud are clearly getting more dense than others. Some parts of the cloud are drifting away. Let's zoom in a little bit. We can see that some parts are getting very dense, and when they get dense and hot, then the conditions are right for nuclear fusion to take place, and we get the birth of a star. So each of these little white dots that you can see popping up is the birth of a new star, because the collapse of the cloud produced pressures and temperatures that are high enough for nuclear fusion to take place. And you can see after a while it looks like a popcorn machine, producing not just a few hundred, but probably thousands of stars. Some of those have a velocity high enough to throw them out of this star cluster, but a lot of them will stay close to where they were born. If we do a little pullback and a little turn, we get an idea of the structure of the cloud. It's now very much more ragged. Notice that not all of the hydrogen has been used up, but a fair bit has, in order to make all of these stars. So remember, this is just a simulation. This is how we think a star is born, usually not in isolation, but along with a few hundred, if not a few thousand siblings in a star cluster. If that's what the simulation is telling us, does this collection of white dots here look anything like the star clusters that we see when we look out into the Milky Way? Well, if we have a look at an image of a star cluster, well, yeah, on the whole, it does. Here we're not seeing the hydrogen cloud, we're seeing the stars that were born from the hydrogen cloud. So these simulations do seem to give us a good handle on why stars are born in clusters. It's probable that our sun was born in a cluster, but it was one of those stars that had enough velocity when it was made that it's actually drifted away from the star cluster, and it's now almost impossible to tell which star cluster was actually the birthplace of our sun. In order to understand what's going on inside a star, we have to understand a few basic concepts. Gravity, we know, is trying to pull everything towards the center. But it's not winning simply because nuclear fusion in the center is generating radiation which is effectively pushing outwards. So gravity is always trying to pull the star together, and the nuclear radiation at the core, the fusion that is fusing hydrogen into helium in the case of our sun, is pushing outwards. And all stars are a balance between these opposing forces, gravity pulling in and radiation pushing out. When these opposing forces are balanced, then the star is stable. But if these forces ever get out of balance, then the star must evolve. And many aspects of star birth, star life, and star death can be explained in terms of those balance and what I like to think of as the ABC of star evolution. So let me tell you what the ABC are, and then we'll go on to think about how that helps us understand evolution. I've said that the nuclei of atoms are positively charged. If we take an atom, strip away the electrons, what's left is positively charged. And if we want these two to fuse together, if we want to push them together and make them fuse into heavier elements, well, if they're both positively charged, because like charges repel, we first have to overcome that repulsion. And we do that by getting the pressure and the temperature high enough. We give the nuclei enough energy that eventually we can push them together. So high temperatures and high pressures can accelerate the fusion process. That is the A of the ABC. The B, well, we've already seen that. A star in equilibrium means that gravity pulling in and radiation pushing out are in balance. So the B represents balance. And finally, C. Compression produces heat. If we can compress the matter in a star, then it gets hotter. This is no surprise because anybody that's ever compressed any air, for instance, pumping up a bicycle tyre, what happens when you compress the air and pump the tyre up? Well, the air and the bicycle pump get hot. Compression produces heat. So there are the A, B, C, and we'll see how they relate to each other in just a moment. When we're talking about stars, and in particular how stars evolve, it's quite useful to refer back to this diagram, the so-called Hertzsprung-Russell diagram. It's a diagram where stars are plotted with their luminosity on the vertical scale, usually written as the luminosity compared to how bright the sun is, and the horizontal scale is the surface temperature of the star. For historical reasons, the colder stars are on the right and the hotter stars are on the left, as indicated by the scale at the bottom there. So our sun is somewhere near the middle, and it has a luminosity of 1 by definition, because it's the luminosity relative to how luminous the sun is, and the surface temperature of the sun is just a little shy of 6,000 Kelvin. So there's the position of the sun, and we'll refer back to this diagram a few times. So the evolution of stars depends on how massive the star is. The mass of a star determines its life. High mass stars, meaning stars that are, let's say for the sake of argument, 10 times the mass of our sun, you might say, well, they have a huge amount of fuel, so presumably they live for longer than our sun, because they have more fuel, more nuclear fuel. But actually, because they're more massive, the gravitational forces are much stronger. And if the gravitational forces are stronger, that means in order to stay in balance, they need a huge amount of radiation to be generated at the core. And that means the nuclear fuel gets used up at a really fast rate in order to produce the radiation to balance the very strong forces of gravity because of the high mass. So even though it's got more fuel, it uses it at such a high rate, its lifetime can be much shorter. Our sun might live for quite a few billion years, but a high mass star might only live for a few million years. That might still sound like a long time, but remember, a million years isn't long enough, for instance, for life to evolve on the planets going around a star. If we take the other end of the mass spectrum, what happens in a low mass star? Again, naively, you might say, well, it's a low mass star, there's not much fuel there, it's not going to live very long. Actually, it's just the opposite. Because it's low mass, the gravitational forces are relatively weak. So it doesn't take much radiation to balance those gravitational forces. And if the radiation forces don't have to be very strong, that means the nuclear fuel actually lasts quite a long time. For stars whose mass is, let's say, 1/10 of the mass of our sun, we're not even sure what happens when they die, because it hasn't yet happened. The universe is only 13.8 billion years old, and these low mass stars might last for lifetimes of hundreds of billions or even trillions, perhaps even tens of trillions of years. So these are very long-lived stars, and we can calculate what we think is going to happen when they die, but we've never actually seen it happen. Before I go any further, let me just take a little bit of an aside and remind people that what we're talking about when we talk about big stars and small stars is stars with a large mass and stars with a small mass. Stars with 10 times the mass of our sun, or perhaps as much as 100 times the mass of our sun. And low mass means 100 times smaller, or perhaps 10 times smaller. But how does that equate to physical size? What about the diameter? Well, let me show you by showing some pictures, which I've borrowed from somebody else. Just a reminder that the sizes of planets in the solar system, this is not, of course, in the order they are from the sun, it's in order of their size. Mercury the smallest, then Mars, Venus and Earth. And if we take Earth from the right-hand side of the top panel and place it in the bottom left of the bottom panel, there's Earth relative to the sizes of Neptune and Uranus, the ice giants, and then there's the huge Saturn and the even larger Jupiter. So this is just a starting point to remind us how big the planets are. Let's do the same thing again. Let's take Jupiter from the right-hand side of the last panel and place it on the left-hand side of the next panel. So there's Jupiter in the bottom left. And there's a small star called Wolf 359 next to it. Then there's our Sun, and then there is Sirius. Notice that large planets are not so much different in size from small stars. In other words, you could say if Jupiter was a lot bigger and a lot more massive, it would actually turn into a star. Well, that's not likely to happen, but yes, the largest planets are not so different from the smallest stars. So there's our Sun, very much bigger than the smallest star, but still classified as a dwarf on the grand scale of things. And there's Sirius, which looks quite big compared to our Sun. Let's go a step further. Let's take Sirius from the right-hand side and put it on the left-hand side of the next panel. So there's Sirius and a few other stars, Pollux in the constellation of Gemini, Arcturus and Aldebaran. So clearly Arcturus and Aldebaran are huge compared to Sirius, which remember is larger than our Sun. So Arcturus and Aldebaran are red giant stars. Ultimately our Sun will eventually swell up until it's this sort of size. But we're not done yet. Aldebaran isn't the largest star we know about. Let's take Aldebaran and put it on the left-hand side of the next panel. There's Aldebaran, the even larger Rigel, and by comparison, the absolutely huge Antares and Betelgeuse. These are red supergiants. Betelgeuse is not the largest star we know of. It's getting there. It's one of the biggest we know about. And the record for the largest star does change from time to time. But here we see Betelgeuse on the left-hand side compared to a few stars which, as of a few years ago, were thought to be the largest stars in existence. We now have a few other candidates. I don't think VY Canis Majoris is any longer considered the largest star we've discovered, but it'll do for the sakes of this particular presentation. So you can see there is an absolutely enormous range of the physical size, the diameter of stars, even though the masses are usually not much greater or much less than the Sun, the physical sizes can vary enormously. And if we wanted to compare the Sun to the one on the right hand side there, VY Canis Majoris, we can do that. There's the Sun, and if I show VY Canis Majoris to scale, well, perhaps you're having a little difficulty figuring out where it is. Okay, in it comes. There we go. I can't fit it all in. Now this actually is a little bit of an exaggeration. I haven't exaggerated the size of VY Canis Majoris. I've actually exaggerated the size of the Sun. If I plotted the Sun to its true size relative to VY Canis Majoris, the Sun would actually occupy a dot, probably smaller than a pixel on the either the iPad screen or the projector screen that you're looking at. So I've made the Sun slightly bigger in order that you can actually see it. So again, you can see there's an enormous difference between the smallest of stars and the largest of stars. But bear in mind, it's not the physical size, it's the mass that determines its evolution. So we can return to the question, okay, stars might live a long time or a short time, but what happens when the fuel runs out? So nuclear fusion, sometimes that's called somewhat confusingly burning. We're not talking about burning in the same sense as a lump of coal or wood would burn in the Earth's atmosphere. We're talking about burning in the sense of taking subatomic particles like protons, fusing them together and building up heavier and heavier elements. But when we fuse particles together, when we fuse the nuclei of atoms together, we don't use up much of the star's mass. As I said earlier, in the case of our sun, every second of its life, it's fusing 620 million tons of hydrogen to make 616 million tons of helium. Every second, 4 million tons is lost, i.e. converted from mass into energy, and that energy is radiated out from the core. That's what's keeping the Earth lit and warm. The light and heat from the sun are the result of that 4 million tons being lost every second. But it's only 4 million out of 620 million. Even after the 10 billion year lifetime of the sun, 99 and a bit % of the mass is still there. Only about 0.5% of the mass of the sun is lost in the process of turning hydrogen into helium. In that sense, it's a very inefficient process. And yet it's enough to keep all of the planets in the solar system bathed in sunlight for some 10 billion years or so. So we can ask the question, in the case of our sun or in other stars, what happens when the hydrogen runs out? That's where we come to the ABC. So let's have a look at what happens. If the hydrogen starts to run out, that means the radiation in the core starts to drop. And remember the balance? Generally, for most of its life, the star is in balance. But if the hydrogen runs out, the radiation drops, which means gravity is now stronger than radiation. The star is out of balance. So if gravity is stronger than radiation, the star will shrink. Remember the C? Compression produces heat. So if the star shrinks, the compression will heat up the core, and that will allow the acceleration of the fusion process. It forces nuclei together, even though they're positively charged and don't want to get any closer. So heating up the core accelerates the fusion process and can start to fuse not hydrogen into helium, but it can start to fuse helium into heavier elements such as carbon and oxygen and ultimately other elements in the periodic table. If you start to accelerate the fusion process, you generate more radiation and balance is restored. So that's how the ABC works. In principle, if it happens more than once, you can go round and round that loop multiple times. If you get out of balance, the star shrinks. The compression accelerates the fusion process, which increases the radiation and restores the balance. A, B, C, A, B, C, A, B, C. In principle, a star might go round that loop many times. Here's the periodic table of the elements in a rather cartoony form. Let me just dim that down as it's a bit frantic and remind ourselves that hydrogen is up there at the top of the periodic table, which can be fused to make helium up there in the top right-hand part of the periodic table. And if we go through that ABC process more than once, then we can fuse helium into carbon and oxygen and other elements like neon and silicon. And we can do that all the way up to that element outlined in red, iron, element number 26. But it happens to be an observation that we've made of nuclear elements that we can't get energy out of fusing elements beyond iron. If we fuse hydrogen or carbon or oxygen or silicon and make heavier elements, we get energy released, but not if we try and do it with any elements heavier than iron. So if the process I've described up till now explains where all the elements come about, how they come about, but it doesn't work beyond iron, how do we explain the heavy elements that we see on Earth, such as silver and gold and lead, for instance? If they're not coming from the fusion factories that we've been describing, where do they come from? Why does gold exist? Well, I've said hydrogen can be fused to make helium, and then helium to make carbon. Carbon makes neon, and so on, all the way up to iron. I'm not going to talk about the nuclear physics, but we have found from experiments here on Earth that when you start to fuse elements, and here the horizontal scale represents the mass of different elements, when we fuse elements we get a certain amount of energy out until we reach iron, the top of this curve. And when we go beyond iron, if we start fusing iron into heavier elements, we don't get energy released. We need an input of energy to force iron to fuse into heavier elements. So again, we have the question, if that's the case, where do the heavy elements come from? Well, we can't simply say stars are fusion factories. We have to look beyond star life and look at star death. For a medium mass star like our Sun, not much heavier, not much lighter, gravity may not be strong enough to hold on to the outer layers of the star when helium starts to fuse into heavier elements, or if you prefer, when helium starts to burn. So once the hydrogen has been used up and the star compresses and helium starts to fuse, it can actually swell out the outer part of the star because gravity isn't strong enough to hold on to the outer layers of the star. The star can expand and the outer layers will cool and start to go red. The star becomes a red giant. And in our diagram that I pointed to earlier, red giants are there. They are further to the right of the Sun because they're cooler, and remember, the temperature is cool on the right and hot on the left. So red giants are to the right of the Sun, and they're above the Sun because red giants, despite being a little bit cooler, they are much larger, a much larger surface area to radiate energy, and hence they are more luminous. Hence they are further up in this diagram. It is possible that when helium burns in the core, the star becomes unstable, and not only does the star swell up because gravity might not be strong enough to stop the outer part of the star expanding, it is possible that the outer layers have enough energy that they leave the star completely. They can be blown off, and the outer layers of the star literally cannot be held on to. This leads to the formation of a planetary nebula. Nothing to do with planets, it's just the name given to what happens when a star loses its outer layers. What's left behind is effectively the core of the original star, which is very much hotter, smaller but hotter. This is a white dwarf, and we can see the white dwarfs there in this diagram. They are hot because they are effectively the core of the Sun after it's lost its outer layers. So they are further to the left of the Sun in this diagram. But they're not very large because it's only the core of the Sun. And if they're not large, they haven't got a very large surface area. So even though they start life quite hot, they've relatively small area, so they're not that luminous. Hence they are in general further down in this diagram compared to the Sun. So red giants to the top right, white dwarfs to the bottom left of this diagram. And some planetary nebula produce spherical shells of gas. The original star at the center of this particular image, that star has shrugged off its outer layers and produced this rather nice planetary nebula. And you can see why you might confuse it with a planet. In a small telescope, an object like this might be confused with the disk of a planet. But not many planetary nebula are actually so regular or symmetric as this. Many planetary nebula have very complex structures, and we are still trying to understand why it is that some of these planetary nebula have such a complicated structure. It's probably related to the way the stars are rotating. It might be that the star is part of a binary system, producing a very interesting structure as its outer layers are slowly removed. High mass stars don't necessarily shrug off their outer layers because the gravity is strong enough in a high mass star to hold the star together beyond hydrogen being fused into helium, beyond helium being fused into carbon, even beyond carbon being fused into heavier and heavier elements. If the star is massive enough, all of these cycles can be going on inside the star without the star blowing up in the same way it would with a lower mass star. What happens when a high mass star comes to the end of its life? Well, that is what happens when eventually you make heavier and heavier and heavier elements until you get to iron. You can't fuse iron to release energy. It can no longer provide the energy to support the star. So what happens when you start making iron in the core? The star collapses. The star core undergoes a catastrophic collapse, and the core gets crushed to the size of perhaps only a few kilometers. In the process, a shock wave rebounds from that core, and that shock wave blasts the rest of the star apart, and the star's material is recycled back into interstellar space. We see the result as a supernova remnant. So here is a Hubble Space Telescope image of the Crab Nebula, the result of a star going supernova, a massive star coming to the end of its life, having produced iron, no longer able to support the star collapses, and eventually the shockwave blasts most of the material of the star into space. This image of a supernova remnant was taken by Hubble in 2005, and it was re-imaged relatively recently by the James Webb Space Telescope in 2023. And if I flick backwards and forwards between these two images, taken approximately 20 years apart, just concentrate on one little feature, perhaps this feature here on the right-hand side of the nebula. If I flick backwards and forwards, you perhaps notice that the nebula as seen by James Webb is a little bit bigger than the nebula as seen by Hubble. That's Hubble, James Webb. An old image, a new image. The stars have been very carefully aligned in these two images, so the difference between Hubble 20 years ago and James Webb relatively recently, that represents a genuine expansion of the nebula. This star went supernova about 1,000 years ago, according to the Earth calendar of when the light actually reached us. And the fact that the James Webb image shows the nebula about 2% bigger is consistent with the idea that this actually exploded 1,000 years ago, and so 20 years represents about 2% of that time period, and hence the nebula is about 2% larger now than it was 20 years ago. The energy of a supernova is absolutely mind-boggling. You can do a back-of-the-envelope calculation and say, how much energy do you need to rip a star apart? And it turns out the energy you need is that number. Now, I know that non-physicists don't get on with energy units of joules, and you've got no idea what 10 to the power 44 joules actually is. But we can get a feel for it by saying, well, let's imagine the total energy output of the sun, not simply the small amount that the Earth receives, but think about the total energy output of the sun sent in all directions, and let's add it all up for each and every second of its 10 billion year lifetime. Now imagine all of that energy being released in just a fraction of a second. That effectively is what we're talking about in a supernova. The word explosion just isn't big enough to get across just how much energy is released in such a short time. In the chaos of a supernova explosion, nuclei will fuse together. In other words, the supernova provides the energy that allows you to fuse elements heavier than iron. You don't get energy out. The supernova provides the energy that allows elements heavier than iron to be fused together. All of the elements generated during the star's life, and any elements that are generated in the process in its spectacular death, are ejected into interstellar space and effectively recycled. So the heavy metals found on Earth were made as a result of a supernova, meaning that the sun cannot have simply been made out of hydrogen. All of the elements on Earth must have been made from stars that have been through many, many generations. Probably not a second generation star, not even a third or fourth, maybe a fifth, sixth, seventh, eighth generation star. Stars, who knows which stars, born, lived, died, and supernova generated heavy elements that were then seeded into space and ultimately gave rise to the sun and the various planets, and that's why we see heavy elements on the Earth today. After a supernova has crushed its core, and remember the shock wave then rips all of the star's outer regions apart, what happens to the star's core that's been crushed? Well, it will end up as a tiny star, only a few kilometers or so in diameter, a neutron star, an object with a mass similar to the mass of our sun, but only kilometers in diameter. It's difficult to imagine the density that would be involved in some object like that. It's thought now that neutron stars, not only being the leftovers of supernova, when one neutron star might happen to collide with another, that is such an energetic collision that the collisions of neutron stars will also generate heavy elements. And at the moment, people are trying to figure out how many of the heavy elements are made by the supernova explosion itself, and how many of the heavy elements are made by the neutron stars that are left over from supernova explosions. That is still an active area of research. But we do know that neutron stars have a mass similar to our sun and are very compact and have very strong magnetic fields. And it is possible that radio emissions from these neutron stars, which we know are spinning quite rapidly. Remember what happens when an ice skater brings their arms much closer together. When you make an object more compact, if it's spinning in the first place, it'll spin even faster when you concentrate the mass closer to its axis of spin. So if you start with a star and then compress it to only a few kilometers, neutron stars spin really fast. And the magnetic field results in a searchlight effect in the sense of any radio emission can be beamed out, and as the neutron star spins, the radio beam might pass the Earth, and we get a radio burst every time the neutron star spins once. And we can take those radio emissions and change them into an audio signal to get an idea of just how fast stars are spinning. So here I'm going to play the sounds. Remember, they're not real sounds, they're just radio emissions which have been turned into an audio soundtrack that tell you just how fast some pulsars, as they're called, are spinning. Neutron stars that are pulsing radio waves. So this is a pulsar by the name of B0329. It spins once in 800 milliseconds, a little bit faster than once per second. But there are other pulsars that are spinning much faster than that. The Vela pulsar, spinning more than 10 times a second. Remember, this is an object with the mass of our sun, but it's spinning 10 times a second. By no means the fastest pulsar we know about. The Crab pulsar, spinning 30 times a second. And I know this is starting to get really irritating. This is now spinning with a period of 5 milliseconds. and one of the fastest that we know of, sounding like a mosquito, with a period of 1.5 milliseconds. Let me stop that because that is particularly irritating. So you can see that some of these objects are spinning really fast because of the spin of the star being whipped up by the fact that it's collapsing from a large object to a tiny object. And that 1.5 milliseconds that I've indicated there at the bottom, that's not the accuracy with which we know the period. We can actually measure the period very accurately, and it's not 1.5 milliseconds, it's actually 1.55780644887275 milliseconds. And we can measure it with that precision, and it turns out that these pulsars are basically more accurate than the atomic clocks we can use to try and time them. Ooh, looks like somebody else wants to be let in. Let me admit them. And looking at lots of pulsars, we can actually use the signals from lots of pulsars to actually check whether our atomic clocks are actually running fast or running slow. And if we have enough atomic clocks giving us a good average, we can start to see whether any pulsars are changing their period or perhaps slowing down. A pulsar might change its period if there's a sudden change. Just like, again, if an ice skater changes the distance from their arms to their center, they will change the rate at which they spin. The same for pulsars. If there's a tiny change of the radius of a star, it'll change the period of its spin. And we can occasionally see that. And we can see stars change every once in a while. But generally speaking, they have very, very reliable and accurate periods that we can measure, as you can see there, to many, 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 many decimal places. It is possible that when a star collapses, it doesn't end up as a pulsar. If gravity wins, if the mass is enough, if we start with a really heavy star, then a neutron star, which is essentially a star with the density the same as a subatomic nucleus, well, it is possible that if gravity is strong enough, it'll be crushed to an even smaller object than that. An object so small that light cannot escape. A so-called black hole. So we know that black holes exist, or at least we can infer their existence from the way stars move and from what's going on at the center of our galaxy and the center of other galaxies. This is a radio image of what's going on close to the center of the galaxy M87. We think there's a black hole right at the center, and we're looking at the so-called accretion disk, the amount of gas and dust that's collecting close to the black hole, in a sense waiting its turn to get sucked into the black hole itself. The black hole at the center, which we can't see, but that shadow in the middle, we think that's surrounding the black hole. We think this black hole has a mass of some 6.5 billion times the mass of our own sun. And if we look at what's going on at the center of our own Milky Way, our Milky Way has got a rather less massive black hole, but still 4 million solar masses, huge compared to an individual star, not as big as the supermassive black hole at the center of other galaxies. And we also see an accretion disk. We see these hot spots. We think material is circulating around this black hole. Again, we can't see the black hole itself. That's somewhere in the middle of this shadow region in the middle. But this sort of donut shape indicates that a lot of material is circulating around the black hole. And if we were to make repeated measurements of what's going on here, we would presumably see the material rotating slowly around the black hole itself. So there's still a lot we don't know about black holes, mainly because no light can ever be emitted from such an object. We can see what's going on in the vicinity of a black hole, but we can never get light from the black hole itself. So we don't know what's going on in there. This object is smaller than a neutron star, but we don't know if it has a finite size or whether it's been completely crushed out of existence and effectively is infinitely dense, a so-called singularity right at the heart. Still a lot of work to be done to understand what's going on there. So let me summarize graphically what I've been saying this evening. Around the Milky Way and probably every other galaxy, there are large clouds of hydrogen. Some of those clouds might collapse and form stars similar to our own sun. Those stars might live for many billions of years, and eventually when the hydrogen runs out, the fusing of helium can give rise to energy that can puff out the star, and the outer layers, depending on the amount of gravity trying to hold them in, the outer layers can puff up into a red giant. If the star has difficulty holding on to its outer layers, those outer layers may be released and form a so-called planetary nebula. Effectively, it's just the outer layers which have been sloughed off and expand into the interstellar medium, leaving a tiny white dwarf behind. The white dwarf being the hot core of the star that's left when its outer layers have been removed into a planetary nebula. So that's the probable fate of our sun in about 5 billion years or so. It is possible that the collapse of a cloud on the left-hand side might produce some larger stars. Trying to understand what is the mass distribution when a cloud collapses, how many small stars does it make, how many large stars does it make, that again is an active area of research. But if a cloud produces a much more massive star, then the star will not live as long. Remember, live fast, die young. And when the star comes towards the end of its life, it could swell up into a red supergiant. And if the star is massive enough such that the hydrogen fusion into helium and then fusion into carbon and then fusion into heavier elements, if that eventually reaches iron, the star can no longer support itself from nuclear fusion, and then you get a collapse of the star and the shock wave blasts the material of the star out into the interstellar medium, a supernova. The star itself, the very core of the star, is crushed down to either the size of a few kilometers to make a neutron star, or is crushed even smaller, and we don't know how big that would be other than it's smaller than a few kilometers, and we end up with a black hole. But in either case, notice that before we even think about white dwarfs and neutron stars and black holes, most of the mass of the star itself is recycled either via a planetary nebula or a supernova. It is recycled back into the interstellar medium. So in other words, the cloud of hydrogen becomes enriched with a few extra heavy elements. And then we go round the cycle again, making some small stars or making some large stars. And at the end of their life, they produce heavier elements, which again get recycled back into the cloud. And our sun was made from a cloud which had a little bit of the heavier elements, and that's why we see the Earth with heavy elements as well as the lighter elements spread throughout the Earth's crust. So there are still some details of stellar evolution that we are working on. There's plenty of people who are studying the real nitty-gritty detail of how stars evolve, how they're born, how they live, and how they die. But we can get a pretty good idea, at least we get the big picture of how stars live by thinking about the A, the B, and the C of stellar evolution. Thank you for listening.